Right now, inside every atom in your body, something impossible is happening. Protons are packed together so tightly they are almost touching, and every single one of them carries a positive electric charge. They should be blasting apart. The electromagnetic force between two protons crammed into a nucleus is trying to shove them away from each other with enormous violence. And yet they stay. Something is overpowering one of the fundamental forces of nature and holding your atoms together. The answer involves a particle most people have never heard of, one built from matter and antimatter fused together, one that survives for less than 30 billionths of a second before it vanishes completely. It has no permanent address inside the atom, and yet, without it, every nucleus heavier than hydrogen would rip itself apart, and the universe as you know it could not exist. If you find this kind of deep dive into the hidden machinery of the universe interesting, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference. Now, let's begin. You are made of atoms. Everything around you is made of atoms. The chair you are sitting in, the air you are breathing, the screen you are looking at right now. And every one of those atoms has a nucleus at its center, a tiny, dense core where almost all the atom's mass is concentrated. You probably learned this in school. It seems simple, ordinary even. But here is what most people never stop to think about. The nucleus should not exist. That is not an exaggeration. It is not a metaphor. Based on what we know about the fundamental forces of nature, atomic nuclei heavier than a single hydrogen atom should tear themselves apart the instant they form. The fact that they do not, the fact that they hold together and stay together for billions of years, means something extraordinary is happening inside every atom you have ever encountered. Something powerful enough to overpower one of the most fundamental forces in the universe. And for decades, nobody could figure out what it was. To understand why the nucleus should be impossible, you need to understand one simple rule about electric charge. Like charges repel. If you have ever played with magnets, you have felt this. Try pushing two north poles together and they shove each other away. Electric charges do the same thing. Two positive charges push apart. Two negative charges push apart. Only opposite charges attract. This is the electromagnetic force, one of the four fundamental forces of nature, and it operates everywhere in the universe, at every scale, without exception. Now think about what sits inside a nucleus. Protons. Every proton carries a positive electric charge. In a hydrogen atom, there is just one proton in the nucleus, so there is no problem. There is nothing for it to repel against. But the moment you move to heavier elements, you start packing multiple protons together. Helium has 2 protons in its nucleus. Carbon has 6. Iron has 26. Gold has 79. Uranium has 92. All of these protons are positive. All of them are repelling each other electromagnetically. And they are not doing it from across the room. They are crammed together into a space so small that it defies imagination. The nucleus of an atom is roughly 1 to 10 femtometers across. A femtometer is 1 quadrillionth of a meter. To put that in perspective, if you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the center of the field. Everything else, the vast majority of the atom's volume, is empty space, with electrons orbiting far away. The nucleus is extraordinarily tiny, and inside that tiny space, protons are separated by distances on the order of 1 femtometer or so. At those distances, the electromagnetic repulsion between two protons is ferocious. If you calculate the force using Coulomb's law, the equation that describes how electric charges push and pull on each other, you get a number that sounds absurd. 2 protons, separated by 1 femtometer, repel each other with a force of roughly 230 newtons. That is about 50 pounds of force. 50 pounds. Between two particles so small that billions of them could fit on the period at the end of this sentence. That tiny pair of protons is pushing apart with the force it would take to lift a medium-sized dog off the ground. And it is not just two protons. In a gold nucleus, 79 protons are jammed into a space roughly 14 femtometers across. Each one is repelling every other one. The total electromagnetic energy trying to blow that nucleus apart is enormous. Every nucleus with more than one proton exists in a state of violent internal conflict, an electromagnetic civil war that should rip it to shreds. And yet nuclei hold together. They hold together for billions of years. The gold atoms in a ring on someone's finger have had those 79 protons packed together since before the Earth formed, since before the Sun ignited, since the cataclysmic collision of dead stars that forged those atoms and scattered them into space over 4.5 billion years ago. Those protons have been sitting together, repelling each other with tremendous force for longer than the solar system has existed, and they have not come apart. Something is holding them, something stronger than the electromagnetic force. But what? For most of human history, nobody even knew the nucleus existed, let alone that it had this problem. The ancient Greeks imagined atoms as tiny, indivisible spheres. That idea persisted for over 2,000 years. In the 1800s, chemists proved atoms were real, but they still imagined them as solid little balls. Then, in 1897, J.J. Thomson discovered the electron, a negatively charged particle much lighter than an atom. This meant atoms had internal structure. They were not indivisible after all. Thomson proposed that atoms were like a pudding of positive charge, with electrons embedded in it, like raisins in a cake. The positive charge was spread out uniformly, and the electrons sat inside it. This was called the plum pudding model, and for about a decade, it was the best picture anyone had. Then Ernest Rutherford changed everything. In 1911, Rutherford and his colleagues Hans Geiger and Ernest Marsden performed one of the most important experiments in the history of physics. They fired tiny, fast-moving alpha particles, which are essentially helium nuclei, 2 protons and 2 neutrons bound together, at an extremely thin sheet of gold foil. If Thomson's plum pudding model was correct, the positive charge in each gold atom would be spread out over the entire atom. The alpha particles, which are dense and energetic, should punch right through with only slight deflections, like throwing bowling balls through a cloud of cotton candy. Most of the alpha particles did pass straight through. This was expected. But then something shocking happened. A small fraction of the alpha particles bounced back at large angles. Some of them came almost straight back toward the source. Rutherford was stunned. He later said it was as if you fired an artillery shell at a piece of tissue paper, and the shell came back and hit you. This made absolutely no sense under the plum pudding model. The only explanation was that the positive charge in each atom was not spread out. It was concentrated in an incredibly tiny, incredibly dense region at the atom's center. The alpha particles that bounced back were the ones that happened to come close to this dense core. The vast majority sailed through the empty space that makes up most of the atom and were barely deflected at all. This was the discovery of the atomic nucleus, and it immediately created a puzzle. If all the positive charge is concentrated in a tiny space, then in any atom with more than one proton, those protons are extremely close together. The electromagnetic repulsion between them should be enormous. The nucleus should fly apart. Why does it not? The puzzle deepened in 1932, when James Chadwick discovered the neutron. The neutron is a particle with almost the same mass as a proton, but with no electric charge. Chadwick showed that nuclei contain both protons and neutrons. This helped explain why nuclei are heavier than their proton count alone would suggest. Helium, for instance, has 2 protons and 2 neutrons. Carbon has 6 of each. The neutrons add mass, but no additional electromagnetic repulsion, since they carry no charge. But the neutron's discovery did not solve the binding problem. If anything, it made it more puzzling. Neutrons do not have electric charge, so there is no electromagnetic attraction between neutrons and protons that could hold the nucleus together. And there is certainly no electromagnetic attraction between protons. So what binds protons to neutrons? What binds neutrons to each other? What is the glue? Gravity is far too weak. Gravitational attraction between 2 protons is roughly 10 to the 36th power times weaker than the electromagnetic repulsion between them. That is a 1 followed by 36 zeros times weaker. Gravity is laughably inadequate at nuclear scales. It plays essentially no role inside an atom. The electromagnetic force cannot do it. It is the thing trying to tear the nucleus apart, not hold it together. The weak nuclear force, the only other force known at the time, governs certain kinds of radioactive decay, but does not provide the powerful attraction needed to overpower electromagnetic repulsion at femtometer distances. Physicists in the early 1930s were forced to confront an uncomfortable truth. There must be a force they had not yet discovered. A force that operates only at extremely short distances, distances comparable to the size of the nucleus itself. A force strong enough to overpower the electromagnetic repulsion between protons. A force so powerful that it could glue protons and neutrons together into a stable, long-lived structure, despite the relentless electromagnetic pressure trying to blow them apart. And a force so short-ranged that its effects are completely invisible beyond the tiny scale of the nucleus. This hypothetical force was given a straightforward name: the strong nuclear force, or sometimes simply the strong force. It had to be the most powerful force in nature at the distances where it operates, stronger than electromagnetism, overwhelmingly stronger than gravity. But it also had to have a peculiar property that none of the other forces shared. It had to essentially vanish beyond a distance of a few femtometers. Electromagnetism reaches across the entire universe. Gravity reaches across the entire universe. But this new force had to be confined to the nuclear scale. Outside the nucleus, it is as if it does not exist. This combination, extreme strength at short range and complete absence at long range, was unlike anything physicists had seen before. In 1935, a young Japanese physicist named Hideki Yukawa made a brilliant theoretical leap. Yukawa asked a deceptively simple question. If the strong force exists, what carries it? In physics, forces between particles are mediated by other particles. The electromagnetic force between 2 charged particles is mediated by photons, particles of light. When 2 electrons repel each other, they are exchanging photons back and forth. The photon is the carrier of the electromagnetic force. This was understood through the framework of quantum field theory, which was still being developed in the 1930s, but was already producing remarkable results. Yukawa reasoned that the strong nuclear force must also have a carrier particle. Just as photons carry electromagnetism, some unknown particle must carry the force that binds protons and neutrons together. But here was the key insight. The photon has no mass, and it is precisely because the photon is massless that the electromagnetic force has infinite range. A massless carrier particle can travel any distance, which is why electromagnetism reaches across the universe. But the strong nuclear force has a very short range. It barely reaches beyond 1 or 2 femtometers. Yukawa realized that a short-ranged force requires a massive carrier particle. The heavier the carrier, the shorter the range. This is not just a guess. It follows directly from the uncertainty principle in quantum mechanics. When a proton emits a carrier particle, it is briefly creating mass and energy out of nothing. The uncertainty principle allows this, but only for a very short time. The heavier the particle, the shorter the time it can exist before it must be reabsorbed. And since no particle can travel faster than light, a shorter lifetime means a shorter distance. A massive carrier particle can only travel a tiny distance before it must be absorbed by another nucleon. This means the force it carries only operates over that tiny distance. Yukawa worked out the mathematics. He calculated that for a force with a range of about 1 to 2 femtometers, the carrier particle would need a mass roughly 200 times the mass of an electron. That put it somewhere between the electron and the proton in mass. The electron has a mass of about 500,000 electron volts in energy units. The proton has a mass of about 938 million electron volts. Yukawa's predicted particle would have a mass of roughly 100 to 200 million electron volts. Nothing known at the time had a mass anywhere near this value. The only elementary particles known in 1935 were the electron, the proton, the neutron, and the photon. None of them fit. Yukawa was predicting an entirely new particle, one that had never been observed. This was an extraordinary act of theoretical physics. Yukawa did not start with a particle and try to figure out what it does. He started with a force whose existence was demanded by the behavior of nuclei, worked out what kind of particle must carry it, and predicted that particle's mass. If such a particle could be found, it would confirm the entire picture. The physics community took notice, and then, just 2 years later, something was found. In 1936 and 37, Carl Anderson and Seth Neddermeyer, studying cosmic rays using cloud chambers, discovered a new particle with a mass of about 106 million electron volts. This was close to Yukawa's prediction. The excitement was immediate. Had they found Yukawa's carrier of the nuclear force? The new particle was initially called the mu meson, or simply the muon. For nearly a decade, many physicists assumed the muon was Yukawa's predicted particle. It had roughly the right mass. It appeared in cosmic rays, which have enough energy to produce new particles through collisions in the upper atmosphere. Everything seemed to fit, at least superficially, but something was deeply wrong. If the muon was the carrier of the strong nuclear force, it should interact strongly with protons and neutrons. That is the entire point. A force carrier must interact powerfully with the particles it binds. When muons pass through matter, they should be captured quickly by nuclei, absorbed into nuclear interactions with high probability. But experiments showed that muons do not behave this way. Muons pass through matter almost as if the nuclei are not there. They penetrate deep into materials without being absorbed. They sail right through blocks of iron and lead as if the strong force does not apply to them. The critical experiment came in 1947, performed by 3 Italian physicists, Marcello Conversi, Ettore Pancini, and Oreste Piccioni. Working in Rome, they studied what happens when muons slow down and stop inside matter. If the muon were the nuclear force carrier, negative muons should be captured rapidly by nuclei once they slow down and get close enough. But Conversi, Pancini, and Piccioni found that in light elements, muons were not captured. They simply decayed on their own, as if the nucleus was irrelevant. The muon did not interact strongly. It was not Yukawa's particle. This was a crisis. Physicists had a beautiful theoretical prediction and a particle with the right mass, but that particle turned out to be the wrong one. The muon interacted with matter only through electromagnetism and the weak force, not through the strong force. The famous physicist Isidore Rabi reportedly quipped when told about the muon, "Who ordered that?" The muon seemed completely unnecessary. It behaved like a heavier version of the electron, participating in electromagnetic and weak interactions, but completely ignoring the strong force. It was a puzzle, and in some ways it still is. Nobody fully understands why the muon exists, or what role it plays in the deeper structure of particle physics. But the story did not end there. The real particle, the one Yukawa had predicted, was found in the same year. In 1947, Cecil Powell and his team at the University of Bristol, including the Brazilian physicist Cesar Latèche, the Italian physicist Giuseppe Occhialini, and Hugh Muirhead, made the discovery using a completely different technique. Instead of cloud chambers, they used specially prepared photographic emulsions. These are thick layers of photographic material sensitive enough to record the tracks of individual subatomic particles. They exposed these emulsions to cosmic rays at high altitude, on mountaintops, where cosmic ray intensity is much greater than at sea level. When they developed the emulsions and examined the tracks under microscopes, they found something new. A particle heavier than the muon, with a mass of about 140 million electron volts, that decayed into a muon and another particle. And crucially, this heavier particle interacted strongly with nuclei. When it encountered nuclear matter, it was absorbed rapidly. It participated in the strong force. This was the particle Yukawa had predicted 12 years earlier. It was called the pi meson, or simply the pion. The name meson comes from the Greek word mesos, meaning middle, because its mass is between that of the electron and the proton. The pion was the carrier of the strong nuclear force between protons and neutrons. It was the glue holding every atomic nucleus together. The discovery of the pion was one of the great triumphs of 20th century physics. Yukawa had predicted it from pure theoretical reasoning, starting from the observed properties of nuclei and working backward to what must exist. Powell's team found it in the cosmic ray debris raining down from the upper atmosphere. The prediction and the discovery matched beautifully. The pion had approximately the right mass. It interacted with nucleons exactly as Yukawa's theory required. It explained why the strong nuclear force has a range of about 1 to 2 femtometers, because the pion's mass limits how far it can travel during the brief quantum fluctuation that creates it. Yukawa was awarded the Nobel Prize in Physics in 1949, the first Japanese citizen to receive a Nobel Prize. Cecil Powell received the Nobel Prize in Physics in 1950 for his development of the photographic emulsion technique and the discovery of the pion. These prizes recognized one of the most remarkable episodes in the history of science: a theorist predicting a particle that must exist based on the behavior of nuclei, and an experimentalist finding it using an ingenious new detection method. But the discovery of the pion also opened a door into a much deeper mystery. The pion explained how the force between protons and neutrons works at nuclear distances. It provided a mechanism. But what was the pion made of? Why did it have the mass it had? Why did it interact so strongly with nucleons and not with electrons or muons? And why, unlike protons and neutrons, did the pion decay so quickly? A free neutron outside a nucleus lasts about 15 minutes on average before decaying. A proton, as far as we can tell, lasts essentially forever. But the pion, the particle responsible for holding every nucleus together, survives for less than 100 millionth of a second before it vanishes. The charged pions last about 26 nanoseconds. The neutral pion lasts less than 1/10 of a femtosecond, which is roughly 84 billionths of a second. That is breathtakingly brief. How can the stability of every atom in the universe depend on a particle that barely exists long enough to cross a single nucleus? How can the force that holds matter together be carried by something so fragile, so fleeting, so fundamentally impermanent? The answer to these questions would require looking inside the Pion itself, and what physicists found there would turn out to be one of the strangest and most beautiful things in all of nature. The Pion is not made of ordinary matter in any familiar sense. It is built from something far more exotic. It is a composite of a quark and an antiquark, matter and antimatter bound together in a single particle. And that composition explains everything about it: its mass, its instability, its role in the nucleus, and why it is unlike any other particle you have ever heard of. By 1947, physicists had their particle, the Pion, the carrier of the nuclear force that Yukawa had predicted 12 years earlier. It had the right mass, roughly 140 million electron volts. It interacted strongly with protons and neutrons. Its mass explained the short range of the force holding nuclei together. But now a much deeper question demanded an answer. What is a pion? Not what does it do, not what force does it carry, but what is it actually made of? What is this thing at the most fundamental level? For 2 decades after its discovery, nobody knew. The pion seemed to be a fundamental particle, a point-like object with no internal structure, just like the electron. But by the late 1960s and early 1970s, a revolution in particle physics revealed that the pion is not fundamental at all. It is a composite object. It is built from smaller pieces, and the nature of those pieces is one of the strangest and most beautiful things in all of physics. But the road to discovering those pieces was long and confusing. The pion was found in 1947, and in the years that followed, it was joined by a flood of other particles. Throughout the 1950s and early 1960s, experiments at particle accelerators and cosmic ray observatories kept turning up new, strongly interacting particles. Not just pions, but kaons, eta mesons, rho mesons, sigma particles, lambda particles, xi particles, delta resonances, and many more. Dozens and dozens of supposedly fundamental particles, each with its own mass, charge, spin, and lifetime. It was chaos. Physicists called it the particle zoo, and the name was appropriate. Nobody could make sense of the menagerie. Were all these particles truly fundamental? Were there really this many basic building blocks of nature? It seemed absurd. When you see that much diversity, you start to suspect there is a deeper pattern, something simpler underneath, generating all the variety. In 1961, the American physicist Murray Gell-Mann and independently the Israeli physicist Yuval Ne'eman found the pattern. Gell-Mann showed that the known hadrons, the strongly interacting particles, could be organized into families based on their quantum properties. He called this classification scheme the Eightfold Way, a playful reference to the Buddhist path to enlightenment. Particles with similar spins but different charges and strangeness quantum numbers fell into geometric patterns when plotted on a diagram. These patterns were not random. They corresponded precisely to the mathematical structures of a symmetry group called SU3. The same way the periodic table of elements hinted at an underlying atomic structure, the Eightfold Way hinted at an underlying substructure inside hadrons. The patterns would make perfect sense if every hadron was built from combinations of a small number of more fundamental objects. In 1964, Gell-Mann took the decisive step. He proposed that all hadrons are made of smaller particles, which he named quarks, borrowing the word from James Joyce's Finnegan's Wake. He proposed 3 flavors: up, down, and strange, each carrying fractional electric charge. No one had ever observed a fraction of the proton's charge. The up quark would carry plus 2/3, the down quark minus 1/3, the strange quark minus 1/3. These fractional charges were unprecedented. Many physicists were skeptical. Quarks might be useful mathematical fictions that organized the particle zoo into neat patterns, but that did not mean they were real physical objects inside protons and pions. The question of whether quarks were real or merely mathematical was answered by experiment. Between 1967 and 1973, a series of landmark experiments at the Stanford Linear Accelerator Center, known as SLAC, provided direct evidence. These experiments used a technique called deep inelastic scattering. The idea was conceptually similar to Rutherford's gold foil experiment from 1911, but at a much smaller scale and much higher energy. Instead of firing alpha particles at gold atoms, physicists fired high-energy electrons at protons. If the proton were a smooth, featureless blob of matter, the electrons would scatter gently, deflecting by small angles. But that is not what happened. Some electrons scattered at very large angles, bouncing hard off something small and dense inside the proton. The scattering pattern revealed that the proton contained point-like objects with fractional electric charges. The electrons were bouncing off quarks. This was the moment quarks became real. Not mathematical abstractions, not convenient fictions. Real physical constituents inside protons and neutrons, carrying the exact fractional charges Gell-Mann had predicted. The experiments at SLAC earned Jerome Friedman, Henry Kendall, and Richard Taylor the Nobel Prize in Physics in 1990. Their work confirmed that protons and neutrons have internal structure. They are not elementary. They are made of quarks. And if protons and neutrons are made of quarks, then so is the pion. The eightfold way classification already told physicists exactly what combination of quarks the pion must contain. The proton is 3 quarks, the neutron is 3 quarks, the pion is 2, 1 quark and 1 antiquark. This was not a guess or an assumption. It was a consequence of the same symmetry structure that organized all the hadrons into families. The pion's place in the classification scheme determined its quark content, and deep inelastic scattering confirmed that quarks are real objects with the properties the classification required. So when we say the pion is made of a quark and an antiquark, we are not stating a hypothesis. We are stating a fact, confirmed by decades of experimental evidence, from the eightfold ways symmetry patterns to the hard scattering of electrons off quarks inside protons at SLAC. The quark model is not speculation. It is one of the best tested frameworks in the history of science. And the pion, as a quark-antiquark meson, sits squarely inside it. The pion is made of a quark and an antiquark. That sentence is short, but it contains an enormous amount of meaning. To understand what it really says, you need to understand what quarks and antiquarks are, how they are different from each other, and what it means to bind them together into a single particle. Quarks are among the most fundamental particles we have ever discovered. As far as any experiment has been able to determine, quarks have no internal structure. They are not made of anything smaller. They are, at our current level of understanding, truly elementary. Quarks come in 6 types, which physicists call flavors. These 6 flavors are called up, down, strange, charm, bottom, and top. Each flavor has different properties, different masses, different quantum numbers. But for understanding the pion, only 2 flavors matter: the up quark and the down quark. These are the 2 lightest quarks, and they are the building blocks of ordinary matter. Every proton and neutron in the universe is made of up quarks and down quarks. A proton is made of 3 quarks, specifically 2 up quarks and 1 down quark. A neutron is also made of 3 quarks, specifically 1 up quark and 2 down quarks. Particles made of 3 quarks belong to a family called baryons. The word baryon comes from the Greek word for heavy, because the first baryons discovered, the proton and neutron, were among the heaviest particles known at the time. Protons and neutrons are baryons. They are 3 quark objects. But the pion is not a baryon. The pion is not made of 3 quarks. It is made of 2, 1 quark and 1 antiquark. This makes the pion a meson. Mesons are fundamentally different from baryons. A baryon contains 3 quarks. A meson contains 1 quark and 1 antiquark. The word meson, as mentioned earlier, comes from the Greek for middle, referring to the fact that mesons were originally discovered with masses between those of the electron and the proton. Now, what is an antiquark? An antiquark is the antimatter counterpart of a quark. For every type of matter particle, there exists a corresponding antimatter particle with the same mass but opposite charge. The electron has the positron, the neutrino has the antineutrino, and every quark has an antiquark. An up antiquark has the same mass as an up quark, but its electric charge is opposite. An up quark carries a positive charge of plus 2/3. An up antiquark carries a negative charge of minus 2/3. A down quark carries a negative charge of minus 1/3. A down antiquark carries a positive charge of plus 1/3. The pion is a quark bound to an antiquark, matter fused to antimatter. This is an extraordinary thing. In everyday experience, matter and antimatter do not coexist peacefully. When a particle meets its antiparticle, they annihilate each other. They convert their combined mass entirely into energy, usually in the form of photons. An electron meeting a positron produces a flash of gamma rays. The particles vanish and pure energy remains. This is the most efficient energy conversion in the universe. Every last bit of mass becomes energy, following Einstein's famous equation E equals mc². And yet, inside a pion, a quark and an antiquark sit together, bound together, held together by the same force that holds quarks inside protons and neutrons, the strong force carried by gluons. They exist in an uneasy partnership, matter and antimatter cohabitating inside a single particle. The quark does not immediately annihilate with the antiquark because they are bound by the gluon field, locked into a quantum state where annihilation is not instantaneous. But the potential for annihilation is always there. It is built into the very structure of the pion. The pion carries within itself the mechanism of its own destruction. This is precisely why the pion is unstable. A proton, which is made of 3 quarks and contains no antiquarks, has nothing to annihilate against. There is no antimatter inside it. As far as we can tell, the proton lasts forever. Its lifetime, if it has one at all, is longer than 10 to the 34th power years. That is far longer than the current age of the universe, which is only about 14 billion years. Far longer than the current age of the universe. The proton is essentially immortal, but the pion is not. The pion contains a quark and an antiquark, and quantum mechanics provides pathways for them to annihilate or to rearrange themselves into lighter particles. The pion cannot last. It is built to self-destruct. The only question is how quickly, and the answer depends on which type of pion you are talking about. There are 3 types of pions, 3 members of the pion family. They are the positively charged pion, the negatively charged pion, and the neutral pion. They are sometimes called pi plus, pi minus, and pi zero. Each one has a different quark composition, a different electric charge, and a dramatically different lifetime. The positively charged pion, pi plus, is made of an up quark and a down antiquark. The up quark has a charge of plus 2/3. The down antiquark has a charge of plus 1/3. Add those together and you get plus 1. The pi plus has a charge of plus 1, in units of the proton's charge. The negatively charged pion, pi minus, is the antiparticle of the pi plus. It is made of a down quark and an up antiquark. The down quark has a charge of minus 1/3. The up antiquark has a charge of minus 2/3. Add those together and you get -1. The pi minus has a charge of -1. The neutral pion, pi0, is more complicated. It is a quantum mechanical mixture of two states. It is partly an up quark paired with an up antiquark, and partly a down quark paired with a down antiquark. In quantum mechanics, a particle does not have to be in one definite state. It can exist in a superposition of multiple states simultaneously. The pi0 is a superposition of these two quark-antiquark combinations. It has no electric charge. Now let us talk about masses and lifetimes, because these reveal something deeply important about the pion's nature. The charged pions, pi plus and pi minus, each have a mass of about 139.6 million electron volts. The neutral pion, pi0, has a mass of about 135 million electron volts. These masses are strikingly light compared to the proton, which has a mass of 938 million electron volts. The pion is only about 15% of the proton's mass. This is remarkable, and it is not a coincidence. The pion's lightness is telling us something deep about the physics of the strong force, something that connects to one of the most profound symmetries in nature. The lifetimes are where things get dramatic. The charged pions live for about 26 nanoseconds. A nanosecond is 1/1000th of a second. So 26 nanoseconds is 26 billionths of a second. That is an incredibly short time by human standards. You cannot perceive anything that happens on this timescale. A blink of your eye takes roughly 300 million nanoseconds. In the time it takes you to blink once, a charged pion could be born, live its entire life, and decay roughly 12 million times over. 26 nanoseconds is a brief existence, but compared to the neutral pion, the charged pion is practically immortal. The neutral pion lives for about 84 attoseconds. An attosecond is 1/quintillionth of a second, 1/billionth of a billionth of a second. 84 attoseconds is so short that light itself only travels about 25 nanometers in that time. That is roughly the size of a large protein molecule. The neutral pion barely exists long enough for light to cross a virus. It is born, and then almost immediately, it is gone. Let those numbers sink in. The charged pion lives about 26 nanoseconds. The neutral pion lives about 84 attoseconds. The charged pion lives roughly 300 million times longer than the neutral pion. 300 million times. These are both pions. They are closely related particles with nearly the same mass, built from the same kinds of quarks. And yet one lives 300 million times longer than the other. Why? The answer lies in how they decay, and that in turn depends on which forces are involved in the decay process. The neutral pion decays through the electromagnetic force. It does not need the weak force to decay. Remember, the pi0 is a quark paired with its own antiquark, an up quark with an up antiquark, or a down quark with a down antiquark. A quark and its own antiquark can annihilate directly through electromagnetic interactions, producing photons. And that is exactly what happens. The pi0 decays into two gamma-ray photons. The quark and the antiquark annihilate each other, their mass converts into energy, and two photons fly off in opposite directions. This process is fast because the electromagnetic force is relatively strong. It does not require any change of quark flavor. It is a direct annihilation, and it happens almost instantly. The charged pions cannot decay this way. In a pi plus, you have an up quark and a down antiquark. These are different flavors. An up quark cannot simply annihilate with a down antiquark through electromagnetism alone, because they are not each other's antiparticle. The up quark's antiparticle is the up antiquark, not the down antiquark. To decay, the charged pion must change one quark flavor into another. and changing quark flavors is the exclusive business of the weak nuclear force. The weak force is the only force in nature that can transform one type of quark into a different type. So the pi plus decays through the weak force. Specifically, the up quark and the down antiquark annihilate through a weak interaction, producing a positively charged muon and a muon neutrino. The pi minus, being the antiparticle of the pi plus, decays into a negatively charged muon and a muon antineutrino. The weak force is enormously slower than the electromagnetic force. It is called the weak force precisely because it is feeble compared to both the strong force and electromagnetism. Processes that proceed through the weak force take much longer than processes that proceed through the electromagnetic force. This is why the charged pion lives 300 million times longer than the neutral pion. The neutral pion decays through a fast electromagnetic process. The charged pion must wait for a slow, weak process. Both are ephemeral by human standards, but one is ephemeral at the level of nanoseconds, while the other is ephemeral at the level of attoseconds. There is something philosophically striking about these decays. When a neutral pion decays into two photons, the mass of the quarks has been entirely converted into pure light. The pion was matter, a composite of a quark and an antiquark, with mass and structure. And then it becomes two photons, which are massless particles of light traveling at 300,000 kilometers per second. Mass has become light. Matter has become energy. It is E equals mc squared, made physical, made visible, happening trillions of times every second throughout the universe. When a charged pion decays, it produces a muon and a neutrino. The muon is itself unstable. It will subsequently decay into an electron, a neutrino, and an antineutrino. So the pion's substance cascades down through a chain of lighter and lighter particles, until eventually you are left with stable particles, electrons, neutrinos, and photons. The pion's brief life ends in a shower of almost ghostly remnants, particles so light and so weakly interacting that they pass through ordinary matter like it is not there. Now, let us return to the pion's mass. 135 to 140 million electron volts. This number is not random. It is connected directly to the range of the nuclear force, and it is also connected to something deep about the structure of the strong force itself. Start with the connection to nuclear force range. Yukawa's original insight was that the carrier's mass sets the force's range, and we will see the precise mechanism for this shortly. For now, the key fact is that the pion's mass of about 140 million electron volts gives the nuclear force a range of roughly 1.4 femtometers. That matches beautifully with the observed size of atomic nuclei and the distances over which nucleons interact. The pion is not just any mass. It is exactly the mass needed to explain why nuclei are the size they are. This is powerful confirmation that the pion really is the carrier Yukawa predicted. But it also raises a deeper question. Why does the pion have this particular mass? Why is it so much lighter than the proton? But why does the pion have this particular mass? Why is it so much lighter than the proton? The proton and the pion are both built from quarks held together by the strong force. You might expect them to have comparable masses, and yet the pion is only about 15% as heavy as the proton. Understanding why requires looking at one of the most profound phenomena in particle physics. The mass of the proton does not come primarily from the masses of its quarks. This is one of the most counterintuitive facts in all of physics. An up quark has a mass of only about 2.2 million electron volts. A down quark has a mass of about 4.7 million electron volts. A proton contains 2 up quarks and 1 down quark. If you add up those quark masses, you get about 9.1 million electron volts. But the proton's total mass is 938 million electron volts. The quark masses account for less than 1% of the proton's mass. Over 99% of the proton's mass comes from something else entirely. That something else is the energy of the gluon field. Inside the proton, quarks are not sitting still. They are zipping around at nearly the speed of light, confined to a tiny space by the overwhelming strength of the strong force. The gluons that bind them are constantly being emitted and absorbed, creating a seething, energetic cloud of gluon field energy. Pairs of quarks and antiquarks are constantly popping in and out of existence inside this cloud. It is a roiling, violent quantum environment. And all that energy, the kinetic energy of the quarks, the energy stored in the gluon field, the energy of virtual quark-antiquark pairs, all of it contributes to the proton's mass. Through E equals mc squared, energy is mass. The proton is heavy not because its quarks are heavy, but because the strong force environment inside it is extraordinarily energetic. Now consider the pion. The pion is also made of quarks and gluons. It is also bound by the strong force. So why is it so much lighter? The answer involves a deep symmetry of the strong force, and the fact that this symmetry is very nearly perfect. If the up quark and the down quark were exactly massless, the strong force would possess an additional symmetry called chiral symmetry. Chiral symmetry, in simple terms, means that the strong force treats left-handed and right-handed quark rotations independently. It is a continuous symmetry, and when continuous symmetries are spontaneously broken, which means the symmetry exists in the laws but not in the ground state, something remarkable happens. A theorem proven by Jeffrey Goldstone in 1961 guarantees that whenever a continuous symmetry is spontaneously broken, a massless particle must appear. These massless particles are called Goldstone bosons. In the real world, chiral symmetry of the strong force is spontaneously broken. The vacuum state, the lowest energy state of the strong force, does not respect this symmetry, even though the underlying equations do. When this happens, Goldstone's theorem predicts the appearance of massless particles. If the up and down quarks were truly massless, the three pions would be exactly massless Goldstone bosons. Zero mass. Three perfectly massless particles, one for each direction of the broken symmetry. But the up and down quarks are not exactly massless. They have small but non-zero masses, about 2 and 5 million electron volts respectively. These small masses explicitly break chiral symmetry by a small amount. The symmetry is not perfect. It is approximate, and so the pions are not exactly massless. They are approximately massless. They are very light compared to other hadrons, but not zero mass. Their mass is directly proportional to the square root of the quark masses. Small quark masses produce small pion masses. This is why the pion is so much lighter than the proton. The proton's mass comes mostly from the energy of the strong force field, which is enormous. The pion's mass comes from a completely different source: the small, explicit breaking of chiral symmetry by the tiny quark masses. The pion is light because it is almost a Goldstone boson. It is the ghost of a broken symmetry, a particle that would be massless in a slightly more symmetric universe, given just a little mass by the fact that quarks are not perfectly massless. This connection between the pion's mass and spontaneous symmetry breaking is one of the most elegant results in all of particle physics. It explains why the pion is light. It explains why the nuclear force has the range it has, and it ties the stability of every atomic nucleus in the universe to a deep, abstract symmetry property of the strong force. Think about what we have established about the pion so far. It is made of a quark and an antiquark. It is a meson. It is inherently unstable because it contains matter and antimatter bound together, carrying the seeds of its own annihilation. It comes in 3 varieties with different charges and wildly different lifetimes. The neutral pion dies almost instantly through electromagnetic annihilation into photons. The charged pions linger for a relatively luxurious 26 nanoseconds because they must decay through the much slower weak force. And the pion's mass, far from being arbitrary, is a consequence of one of the deepest symmetry principles in physics: chiral symmetry breaking in the strong force. The pion is not a building block in the way that protons and electrons are building blocks. Protons and electrons are stable. They last essentially forever. They are the permanent furniture of the universe. The pion is something different. It is a fleeting, transient object, a particle that exists only briefly before decaying into something else. It does not sit around waiting to be used. It appears, does its work, and vanishes. And yet, as we are about to see, this fleeting particle is responsible for the most important job in all of nuclear physics. It is the agent that holds the nucleus together, not by being permanently present, but by being constantly exchanged. The pion is not a permanent resident of the nucleus. It is a messenger, a quantum ghost that flickers in and out of existence between protons and neutrons, and in doing so, creates the force that holds all complex matter together. Understanding how this works, how a particle that barely exists can generate a force powerful enough to overpower electromagnetism, requires understanding one of the most profound ideas in modern physics: the concept of virtual particles and the mechanism of force through exchange. That mechanism is what transforms the pion from an unstable, self-destructing oddity into the most important particle in nuclear physics. Without it, every nucleus heavier than hydrogen would be impossible. The entire periodic table beyond its first entry would not exist. And yet, this indispensable force depends on a particle that cannot survive on its own, a particle made of matter and antimatter fused together, a particle that is born only to annihilate itself. How can something so impermanent hold together something so enduring? So the pion exists, a quark-antiquark particle, inherently unstable, living for a vanishingly brief moment before it self-destructs. The charged pion survives for 26 billionths of a second. The neutral pion barely lasts 84 quintillionths of a second. These are particles that, by every intuitive standard, should be completely irrelevant to the structure of matter. They are too fragile, too short-lived, too impermanent to serve as building material. They are nothing like protons and electrons, which last essentially forever. They are nothing like neutrons, which at least survive for about 15 minutes when free. The pion is gone before it has barely arrived. And yet, this fleeting, self-destructing particle is the reason every nucleus heavier than hydrogen exists. Every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood, all of them are held together by pions. Not by pions sitting permanently inside the nucleus like bricks in a wall, but by pions being constantly, endlessly exchanged between protons and neutrons, flickering in and out of existence in a ceaseless quantum dance. To understand how something so brief can produce something so lasting, you need to understand one of the most profound and counterintuitive ideas in all of physics: the concept of virtual particles and the mechanism of force through exchange. Let us start with something familiar. You are standing in a rowboat on calm water. A friend stands in another rowboat nearby. You throw a heavy ball to your friend. The recoil pushes your boat backward. When your friend catches the ball, the impact pushes their boat backward. The two boats move apart. By exchanging the ball, you have created a repulsive effect. This is a rough analogy for how particle exchange creates force. Two particles tossing a third particle back and forth between them experience a force as a result. In this simple analogy, the force is repulsive, pushing them apart. But quantum mechanics allows something the classical analogy does not. In quantum mechanics, the exchange of certain particles can also produce attraction, pulling the two particles toward each other. The mathematics works out so that the exchange of pions between protons and neutrons produces an attractive force. Not repulsion, attraction. The details of why require quantum field theory, and the calculations are beyond what we can walk through in plain language, but the result is clear and well established. Pion exchange pulls nucleons together. But here is the crucial question. If a pion only lives for a tiny fraction of a second, how can it travel from one proton to a neighboring neutron inside a nucleus? The proton and neutron are separated by roughly 1 femtometer. The pion needs to cross that gap. Even at nearly the speed of light, crossing 1 femtometer takes about 3.3 times 10 to the minus 24 seconds, which is about 3 billionths of a femtosecond. That is an incredibly short time, but it is actually well within the capabilities of a process governed by the Heisenberg uncertainty principle. And this is where the story gets truly strange. The pions exchange between nucleons inside the nucleus are not ordinary pions. They are not the same as a pion produced in a particle accelerator or created in a cosmic ray collision, flying through space, leaving a track in a detector, and eventually decaying into a muon and a neutrino. The pions mediating the nuclear force are what physicists call virtual particles. And understanding what a virtual particle is requires understanding one of the deepest features of quantum mechanics. The Heisenberg uncertainty principle, in one of its forms, says that the uncertainty in a system's energy, multiplied by the uncertainty in the time over which that energy is measured, must be at least as large as a certain fundamental constant, h bar, which is Planck's constant divided by 2 pi. In practical terms, this means that for extremely short periods of time, energy conservation can be temporarily violated. The universe can borrow energy from the vacuum as long as it pays it back quickly enough. The shorter the borrowing period, the more energy can be borrowed. This is not a metaphor. It is a precise mathematical statement about how quantum fields behave, and its consequences have been confirmed by experiment after experiment. A proton sitting inside a nucleus can spontaneously emit a pion. It does not have the energy to create a pion under normal circumstances. Creating a pion requires about 140 million electron volts, and the proton is not spending that energy from its own mass. It is borrowing it from the vacuum. The uncertainty principle permits this borrowing, but only for an incredibly short time. The more massive the borrowed particle, the shorter the time it can exist. For a pion with a mass of about 140 million electron volts, the maximum time it can exist as a virtual particle is roughly 4.7 times 10 to the minus 24 seconds. During that time, travelling at nearly the speed of light, the pion can cover a distance of about 1.4 femtometers. And that, right there, is the range of the nuclear force. It is not a coincidence. The range of the force is set by how far the virtual pion can travel before the uncertainty principle demands it disappear. The pion's mass determines how long it can exist as a virtual particle. How long it can exist determines how far it can travel. How far it can travel determines the range of the force. This is Yukawa's insight made concrete through quantum mechanics. The mass of the carrier particle determines the range of the force it carries. A heavier carrier means a shorter range. A lighter carrier means a longer range. A massless carrier, like the photon, gives a force with infinite range. The pion, with its particular mass, gives a force with a range of about 1 to 2 femtometers, exactly the range needed to explain nuclear binding. The virtual pion is emitted by one nucleon and absorbed by another nucleon before the uncertainty principle's deadline expires. The pion never exists as a free, independent particle flying through space. It is never directly observed. You cannot put a detector between a proton and a neutron inside a nucleus and catch the pion in transit. The pion is a quantum fluctuation, a temporary disturbance in the pion field that connects the two nucleons. It exists only in the sense that its effects are real and measurable. The force it mediates is real. The binding energy it produces is real. The stability of the nucleus is real. But the pion itself, the individual virtual pion traveling from one nucleon to the other, is not something you can isolate or photograph or hold in your hand. It is a feature of the quantum field, not a billiard ball bouncing between two walls. This distinction matters enormously. It is tempting to imagine the inside of a nucleus as a collection of protons and neutrons with little pion particles whizzing back and forth between them, like tennis balls flying across a net. That picture is vivid and easy to visualize, but it is misleading. The reality is more subtle. In quantum field theory, the forces between particles arise from the structure of quantum fields that fill all of space. The pion field is one of these fields. It exists everywhere. Inside the nucleus, the pion field is strongly excited. The protons and neutrons are sources of disturbances in this field, and those disturbances propagate from one nucleon to another, creating the interaction. The virtual pion is a mathematical description of this field disturbance. It is real in the sense that the field disturbance is real, but it is not a little object with a definite position and a definite trajectory, traveling from point A to point B. The great American physicist Richard Feynman developed a powerful way to visualize and calculate these interactions. Feynman diagrams are pictorial representations of quantum field theory calculations. In a Feynman diagram showing the nuclear force, you draw two nucleon lines, representing a proton and a neutron, running forward in time. Between them, you draw a dashed line representing the virtual pion. The pion line connects the two nucleon lines, showing that the pion is emitted by one nucleon and absorbed by the other. This diagram is not a picture of what literally happens in space and time. It is a bookkeeping tool, a way of organizing a very complicated calculation into manageable pieces. But it captures the essential physics beautifully. The force between nucleons arises from the exchange of virtual pions. The mathematics of this exchange gives rise to what is called the Yukawa potential. This is the mathematical expression describing how the force between two nucleons depends on the distance between them. The Yukawa potential has a very specific shape. At very short distances, within about 1 femtometer, the force is strongly attractive. Protons and neutrons within this distance are powerfully drawn toward each other. But as the distance increases, the force falls off very rapidly. It decreases exponentially, much faster than the electromagnetic force, which falls off as the inverse square of the distance. By the time you reach 2 or 3 femtometers, the Yukawa force has essentially vanished. It is negligible, effectively zero. This exponential fall-off is directly tied to the pion's mass. In the mathematical expression for the Yukawa potential, the rate of fall-off is proportional to the pion's mass. A heavier pion would make the fall-off even steeper, confining the force to an even shorter range. A lighter pion would make the fall-off gentler, extending the range. A massless particle would eliminate the exponential fall-off entirely, giving you the familiar inverse square law of electromagnetism and gravity. The pion's mass of about 140 million electron volts sets the characteristic length scale at about 1.4 femtometers. This length scale is sometimes called the Compton wavelength of the pion. It is the natural distance scale associated with the pion's mass, and it sets the range over which pion exchange operates effectively. Now let us think about what this means for actual nuclei. Consider the simplest nucleus beyond hydrogen, deuterium. The deuterium nucleus, called the deuteron, contains one proton and one neutron. It is the simplest bound nuclear system. The proton and neutron are separated by roughly 2 femtometers on average, held together by the attractive force generated by virtual pion exchange. The binding energy of the deuteron, the energy you would need to supply to pull the proton and neutron apart, is about 2.2 million electron volts. That sounds like a small number compared to the pion's mass of 140 million electron volts, but it is enormous compared to atomic energy scales. Chemical bonds, the forces that hold molecules together, involve energies of a few electron volts. Nuclear binding energies are millions of times larger. This is why nuclear reactions release so much more energy than chemical reactions. The forces involved are incomparably stronger. The deuteron is loosely bound by nuclear standards. It barely holds together. If the nuclear force were just a few percent weaker, the deuteron would not be bound at all. Protons and neutrons would not stick together even in the simplest possible combination. This would be catastrophic for the universe as we know it. Without bound deuterium, the chain of nuclear fusion reactions that powers stars could not proceed. Stars fuse hydrogen into helium, but the first step in that process requires protons and neutrons to form deuterium. If deuterium cannot form, hydrogen cannot fuse into heavier elements. Stars would not shine the way they do. Heavier elements would not be created. Carbon, oxygen, nitrogen, iron, none of them would exist. The universe would be nothing but a thin soup of hydrogen gas, cooling forever in the darkness. No stars, no planets, no chemistry, no life. The existence of every complex structure in the universe depends on the nuclear force being strong enough to bind the deuteron, and that force comes from pion exchange. Move to heavier nuclei and the picture becomes more complex, but the essential mechanism remains the same. Helium-4, the most common helium isotope, contains 2 protons and 2 neutrons. It is extraordinarily tightly bound. Its binding energy per nucleon is about 7 million electron volts, much higher than the deuterons. The 4 nucleons are packed tightly together, each one within pion exchange range of every other one. Each pair of nucleons exchanges virtual pions, and the sum of all these pairwise attractive interactions creates a powerful binding. Helium-4 is so tightly bound that it is one of the most stable nuclei in nature. Alpha particles, which are helium-4 nuclei, are emitted intact from radioactive elements because the 4 nucleons cling to each other so tenaciously. But attraction is not the only thing pion exchange does. There is something even more remarkable happening, something that reveals just how strange the quantum world inside the nucleus truly is. When a proton emits a charged pion and a nearby neutron absorbs it, something extraordinary occurs. The proton becomes a neutron, and the neutron becomes a proton. Their identities swap. Think about what this means. A proton, a positively charged particle made of 2 up quarks and 1 down quark, emits a positively charged pion, a pi+, which carries away 1 unit of positive charge. The proton, having lost that positive charge, is no longer a proton. It has become a neutron. The pi+ travels the short distance to the neighbouring neutron, which absorbs it. The neutron, having gained 1 unit of positive charge, is no longer a neutron. It has become a proton. The two nucleons have exchanged their identities. Where a proton once sat, there is now a neutron. Where a neutron once sat, there is now a proton. And a moment later, the process can happen in reverse, swapping them back. Or a pi minus can be exchanged in the opposite direction, producing the same swap. This identity exchange happens continuously, endlessly, as long as the nucleons are within range of each other. This has a profound consequence for how the nuclear force works. Because protons and neutrons are constantly swapping identities through charged pion exchange, the nuclear force does not distinguish between protons and neutrons. To the strong nuclear force, a proton and a neutron are essentially the same particle in two different charge states. This property is called charge independence of the nuclear force. The attractive force between two protons, between two neutrons, and between a proton and a neutron is almost exactly the same, once you subtract the electromagnetic repulsion between protons. The nuclear force treats them democratically, and charged pion exchange is the reason why. Neutral pion exchange also contributes to the nuclear force. When a nucleon emits and reabsorbs a pi zero, or when a pi zero is exchanged between two nucleons, it does not swap their identities. The proton stays a proton. The neutron stays a neutron. But the exchange still generates an attractive force. All three pion types contribute to nuclear binding. The charged pions produce identity-swapping interactions. The neutral pion produces non-swapping interactions. Together, they create the full nuclear force between every pair of nucleons. The continuous swapping of proton and neutron identities means that inside a nucleus, it does not really make sense to point at a particular nucleon and say, this one is permanently a proton and that one is permanently a neutron. At any given instant, a particular nucleon might be a proton. A moment later, after exchanging a charged pion with its neighbor, it might be a neutron. And a moment after that, it might be a proton again. The identities flicker back and forth on timescales too short to observe individually. What we measure is the average. A helium-4 nucleus has 2 units of positive charge on average, so we say it contains 2 protons and 2 neutrons. But at the quantum level, the 4 nucleons are constantly shuffling their identities among themselves. This identity exchange has direct consequences for the process that powers every star in the universe, including the Sun. Stars shine because of nuclear fusion. In the core of a star like the Sun, hydrogen nuclei, which are single protons, are fused together to build heavier nuclei, ultimately producing helium. The first and most difficult step in this chain is getting 2 protons to come close enough for the nuclear force to grab hold of them. 2 protons repel each other electromagnetically because they both carry positive charge. Even at the extreme temperatures inside a stellar core, roughly 15 million degrees, the protons do not actually have enough energy to overcome this repulsion by brute force. The electromagnetic barrier between them is about 1,000 times higher than their typical kinetic energy. What saves the process is quantum tunneling. At close enough range, quantum mechanics allows the protons a small but non-zero probability of passing through the barrier they cannot classically overcome. Once tunneling brings them within about 1 femtometer of each other, the nuclear force takes over and pulls them together. But 2 protons cannot simply bind together into a stable nucleus. A nucleus of 2 protons and no neutrons does not exist. It is unbound. For the fusion process to work, one of the protons must transform into a neutron through the weak force during the very brief moment when the 2 protons are close together. This produces a deuteron, a bound proton-neutron pair, along with a positron and a neutrino. Once the deuteron forms, the nuclear force, mediated by pion exchange, holds it together. Subsequent fusion reactions build on this foundation, adding more nucleons, eventually producing helium-4, the tightly bound nucleus held together by that same ceaseless pion exchange. Every subsequent step in stellar fusion, every reaction that builds carbon, oxygen, and all the heavier elements forged in the cores and explosions of stars, depends on the nuclear force to hold each new nucleus together as it is assembled. And that force is pion exchange. The light and heat of every star in the sky, the energy that warms your face on a summer afternoon, the photons that allow plants to grow and food chains to exist, all of it traces back to nuclei held together by the ceaseless exchange of virtual pions. The pion does not merely hold matter together, it powers the universe. As you go to heavier elements, the nucleus gets larger. Carbon-12 has 6 protons and 6 neutrons. Iron-56 has 26 protons and 30 neutrons. But here is a crucial point. In these larger nuclei, each nucleon does not interact with every other nucleon through pion exchange. It interacts primarily with its nearest neighbors. Because the nuclear force has such a short range, dropping to essentially zero beyond a few femtometers, a nucleon on one side of a large nucleus does not feel the nuclear attraction of a nucleon on the opposite side. It only feels the pull of the nucleons immediately adjacent to it. This is called the saturation property of the nuclear force, and it has profound consequences. It means that as you add more nucleons to a nucleus, the binding energy per nucleon levels off, rather than continuing to increase. Each nucleon contributes roughly the same amount of binding energy, because each one interacts only with a fixed number of neighbors. This is why nuclear binding energy per nucleon peaks around iron and then slowly decreases for heavier elements. It is a direct consequence of the short range of pion exchange. The short range also explains why the nuclear force does not dominate the universe at large scales. If the nuclear force had infinite range, like electromagnetism or gravity, matter would behave completely differently. All matter would be drawn together by an overwhelmingly powerful attractive force. Nothing like the chemistry and biology we know could exist. But because pion exchange only works over 1 to 2 femtometers, the nuclear force is confined to the interior of atomic nuclei. Beyond the nucleus, it is as if the force does not exist. Atoms interact with each other through electromagnetism, through the electric forces between electrons and nuclei. Chemistry is electromagnetic. Biology is electromagnetic. Everything you experience in your daily life, the forces you feel, the interactions between objects, the behavior of light and electricity and magnetism, all of it is electromagnetic. The nuclear force is hidden away inside the nuclei of atoms, invisible at any larger scale, doing its essential work of holding matter together from behind the scenes. Now, it is important to be precise about what the pions are doing inside the nucleus. The picture of pion exchange, as described so far, is sometimes called the one-pion exchange model, or the one-pion exchange potential. In this picture, the dominant interaction between two nucleons is the exchange of a single virtual pion. This is the simplest and most important contribution, but it is not the complete story. In reality, nucleons can also exchange 2 pions simultaneously, or 3, or even more. They can exchange other, heavier mesons as well, particles like the rho meson or the omega meson, which have higher masses and correspondingly shorter ranges. These multi-pion and heavy meson exchanges contribute corrections to the nuclear force, modifying its strength and shape at shorter distances. At very short distances, less than about half a femtometer, the nuclear force actually becomes repulsive. Nucleons resist being pushed too close together. This short-range repulsion is not well described by simple one-pion exchange. It involves more complex interactions, including the exchange of heavier mesons and direct quark-gluon effects. The repulsive core prevents nucleons from collapsing on top of each other. It gives nuclear matter a finite density. Without it, nuclei would collapse to a point. With it, nuclei have a well-defined size, with nucleons maintaining a minimum separation distance. The full nuclear force, including the attractive pion exchange at medium range and the repulsive core at short range, is described by mathematical expressions called nuclear potentials. These potentials capture how the force depends on nucleon separation, spin, and isospin, a quantum number distinguishing protons from neutrons. Over the decades, increasingly sophisticated potentials have been calibrated to match experimental data. The most advanced modern potentials reproduce thousands of data points with extraordinary precision. But here is something crucial to understand. All of these nuclear potentials, even the most sophisticated ones, are effective descriptions. They describe the force between nucleons at the scale of nucleons, without reference to what is happening at a deeper level inside each nucleon. The pion exchange picture is an effective field theory. It works beautifully at nuclear distance scales. It correctly predicts the range of the force, the binding energies of nuclei, the scattering of protons and neutrons off each other, and countless other phenomena. But it is a description that operates at a particular scale, the scale of protons, neutrons, and pions. This idea that a physical theory can be perfectly valid and enormously useful at one scale while being replaced by a deeper theory at smaller scales is one of the most important concepts in modern physics. It is called the effective field theory framework. An effective theory captures the relevant physics at a particular energy or distance scale without needing to know every detail of what happens at smaller scales. You do not need to know about quarks and gluons to calculate nuclear binding energies. Pion exchange gives you the right answer. You do not need to know about nuclear physics to understand chemistry. Electromagnetic interactions between atoms and electrons give you the right answer. Each layer of physics is self-contained and predictive at its own scale, even though deeper layers exist beneath it. The pion exchange model of nuclear forces is one of the great triumphs of this way of thinking. Yukawa proposed it in 1935. It was confirmed experimentally in 1947, and for decades afterward, nuclear physicists used it to explain an enormous range of phenomena. The binding of the deuteron, the properties of heavier nuclei, the way protons and neutrons scatter off each other at various energies, the structure of nuclear matter in neutron stars, the rates of nuclear reactions inside stars. All of this is built on the foundation of pion exchange. But the pion exchange picture also has boundaries. It works at distances of about 1 femtometer and larger, where the relevant degrees of freedom are protons, neutrons, and pions. At shorter distances, below about half a femtometer, the internal structure of the nucleons begins to matter. The quarks and gluons inside the proton and neutron can no longer be ignored. The effective description in terms of pions breaks down, and you need the deeper theory, quantum chromodynamics, the theory of quarks and gluons. Pion exchange is not wrong at these scales, it is simply incomplete. It is a description of the forest that stops being useful when you need to examine individual leaves. Let us pause and appreciate what we have established. The nucleus of every atom heavier than hydrogen is held together by a force arising from the exchange of virtual pions between protons and neutrons. These pions are never directly observed inside the nucleus. They are quantum fluctuations in the pion field, temporary disturbances that propagate from one nucleon to another and create an attractive force. The pion's mass sets the range of this force at about 1 to 2 femtometers. The force is enormously powerful at these distances, strong enough to overpower the electromagnetic repulsion between protons. But it vanishes rapidly beyond a few femtometers, which is why nuclear effects are invisible at atomic and larger scales. The pions doing this work are not permanent objects. They are not structural components of the nucleus in the way that bricks are structural components of a wall. They are more like a constant conversation between the nucleons. Imagine two people standing a few feet apart, continuously tossing a ball back and forth. The ball is never at rest. It is always in motion, always being thrown and caught. If you tried to freeze the scene and point to where the ball is, you would find it somewhere between the two people, in transit. But you could never find it sitting still. It is always part of the exchange. The virtual pions inside the nucleus are like this, except far stranger. They are not even definite objects with definite trajectories. They are quantum mechanical amplitudes, probability waves in the pion field, contributing to the total interaction between nucleons. This means the common image of pions sitting between protons and neutrons, like mortar between bricks, is completely wrong. Pions are not static structural elements. They are dynamic quantum processes. The force they create is not a thing. It is an ongoing quantum event, a continuous exchange that never pauses, never stops, never rests. As long as the nucleons are within range of each other, the exchange continues. When the nucleons are pulled apart beyond the pion's range, the exchange stops and the force disappears. The binding is maintained only through this unceasing quantum activity. And this quantum activity is not something exotic or rare. It is happening right now inside every atom of your body, inside every atom of everything you have ever touched, inside the atoms of the earth beneath your feet, the air around you, the stars above you. Trillions upon trillions of virtual pion exchanges are happening every instant, in every nucleus of every atom in the universe. The stability of all complex matter depends on this continuous, invisible quantum process. Without it, every nucleus would disintegrate. Every atom beyond hydrogen would cease to exist. The periodic table would contain one entry. Chemistry would not exist. Stars would not fuse elements. Planets would not form. Life would be impossible. The pion, a particle so unstable it cannot survive for even 1/1,000,000th of a second as a free particle, is the reason the material universe exists in all its richness and complexity. Not because it lasts, but because it is constantly being remade. Not because it is permanent, but because the exchange never stops. The nucleus does not need a permanent glue, it needs a perpetual process, and the pion provides exactly that. A quantum whisper, endlessly repeated, holding everything together. Everything we have discussed so far, Yukawa's prediction, the discovery of the pion, the mechanism of virtual pion exchange between protons and neutrons, all of it is true, and all of it works. The pion exchange model correctly predicts the range of the nuclear force. It correctly describes how protons and neutrons bind together inside nuclei. It explains nuclear binding energies, scattering experiments, and the structure of nuclear matter. For decades, it was the foundation of nuclear physics, and in many practical applications it still is. But the pion exchange picture, brilliant and successful as it is not the deepest explanation of what is happening inside the nucleus. It is a description that works at a particular scale, the scale of protons, neutrons, and pions. Beneath that scale, there is a deeper layer, a more fundamental theory, and understanding that deeper layer changes how you see the pion, the nucleus, and the strong force itself. The deeper theory is called quantum chromodynamics, or QCD. It is the theory of the truly fundamental strong interaction, not the force between protons and neutrons, but the force between quarks. This distinction is critical. The force that binds quarks inside a proton is not the same force that binds protons inside a nucleus. They are deeply related, but they are not the same thing. The force inside the proton is the fundamental strong force. The force between protons and neutrons is a residual effect, and the pion is the agent of that residual effect. Let us unpack this carefully, because the distinction between the fundamental strong force and the residual nuclear force is the key to understanding why the pion matters, and also why it is not the final word. Inside a proton, 3 quarks are bound together, 2 up quarks and 1 down quark. They are bound by particles called gluons. Gluons are the carriers of the fundamental strong force, in the same way that photons are the carriers of the electromagnetic force. When 2 quarks interact through the strong force, they exchange gluons. The gluon is massless, like the photon, but there the similarity ends. The strong force, mediated by gluons, behaves in ways that are radically different from electromagnetism. In electromagnetism, the force between 2 charged particles is carried by photons, and photons themselves carry no electric charge. A photon does not interact with other photons. It simply carries the force between charges and goes on its way. This makes electromagnetism relatively simple. The carrier of the force does not itself participate in the force. But gluons are different. Gluons carry what is called color charge. Color charge is to the strong force what electric charge is to electromagnetism. It is the property that quarks possess and that the strong force acts upon. But unlike electric charge, which comes in 2 varieties, positive and negative, color charge comes in 3 varieties. Physicists call these 3 color charges red, green, and blue. These names have nothing to do with actual colors. They are just labels, chosen because 3 color charges combine in ways that are mathematically analogous to how 3 primary colors of light combine to make white. Every quark carries one of the 3 color charges. A quark can be red, green, or blue. And here is the critical difference from electromagnetism. Gluons also carry color charge. A gluon carries 1 color and 1 anticolor simultaneously. Because gluons carry color charge, they interact with each other. Gluons attract other gluons. Gluons can emit and absorb other gluons. The force carriers themselves are subject to the force they carry. This self-interaction is what makes QCD so radically different from electromagnetism and so much harder to calculate. The self-interaction of gluons produces a phenomenon with no parallel in electromagnetism. It is called confinement. When you try to pull 2 quarks apart, the force between them does not decrease with distance the way electromagnetic force does. Instead, it stays constant or even increases. Imagine stretching a rubber band. The farther you pull, the harder the band pulls back. The energy stored in the stretched band increases with distance. Eventually, if you pull hard enough, the band snaps. But when the gluon field between 2 quarks snaps, something extraordinary happens. The energy stored in the stretched field is so great that it creates new quark-antiquark pairs from the vacuum. Instead of freeing a quark, you have created new quarks. The energy you invested went into making new matter, rather than liberating the original quark. This is why no one has ever observed a free quark. Quarks are permanently confined inside composite particles. You cannot isolate a single quark, no matter how much energy you use. Every attempt to pull a quark out of a proton simply creates new quarks that immediately bind with the original quarks to form new composite particles. The quarks are imprisoned, and the prison is unbreakable. This is confinement, and it is one of the most remarkable phenomena in all of physics. Confinement has a profound consequence. It means that all particles made of quarks must be color neutral. Just as electrically neutral atoms have equal amounts of positive and negative charge, color-neutral particles have color charges that cancel out. There are 2 principal ways to achieve color neutrality. The first is to combine 3 quarks, 1 red, 1 green, and 1 blue. Red plus green plus blue equals white, which is color neutral. These 3 quark combinations are baryons. Protons and neutrons are baryons. The second common way is to combine a quark with an antiquark. A red quark paired with an anti-red antiquark is color neutral. A blue quark paired with an anti-blue antiquark is color neutral. These quark-antiquark combinations are mesons, and the pion is a meson. More exotic color-neutral combinations exist, such as tetraquarks and pentaquarks, confirmed in experiments at particle accelerators in recent years. But the overwhelming majority of strongly interacting particles observed in nature are either baryons or mesons. The pion's existence as a quark-antiquark meson is dictated by the rules of color confinement. It is the lightest and simplest meson nature can build. Now here is the crucial point. The proton itself is color neutral. All three quark colors are present, and they cancel out. The neutron is also color neutral. So if you are looking at a proton and a neutron sitting near each other inside a nucleus, both of them are color neutral objects. The fundamental color force, the gluon-mediated force that operates between individual quarks, is in some sense already satisfied inside each nucleon. The quarks inside the proton are bound to each other. The quarks inside the neutron are bound to each other. There should be no leftover force reaching from one nucleon to the other. And yet there is. The proton and neutron do attract each other. The nuclear force is real. So where does it come from if both nucleons are already color neutral? The answer is that color neutrality at a distance is not the same as color neutrality at close range. Think about this by analogy with electromagnetism. An atom is electrically neutral. It has equal amounts of positive and negative charge. From far away, an atom looks like it has no charge at all, and the electromagnetic force between two neutral atoms is essentially zero. But when two atoms get very close to each other, close enough that the electron cloud of one atom can sense the arrangement of charges inside the other atom, a weak residual electromagnetic force appears. The positive and negative charges inside each atom are not in exactly the same location. At close range, the detailed internal arrangement of charge matters. The result is a weak attraction between neutral atoms called the van der Waals force. The van der Waals force is not a new force. It is a residual effect of electromagnetism. It arises because neutral objects, when examined closely enough, are not perfectly featureless. They have internal charge structure, and that structure creates weak, short-ranged forces between them. The nuclear force between protons and neutrons is the analogue of the van der Waals force, but for the strong interaction instead of electromagnetism. Each nucleon is color neutral, just as each atom is electrically neutral. But at distances of about 1 femtometer, the internal color structure of each nucleon becomes relevant. The quarks inside one nucleon can sense the quarks inside the neighboring nucleon. The result is a residual strong force, a leftover effect of the fundamental color force that leaks out from each nucleon at very short distances. This residual strong force is what we have been calling the nuclear force throughout this entire discussion, and pion exchange is the most efficient way to describe it at nuclear distance scales. The pion, as a quark-antiquark pair, is the lightest object that can carry strong force quantum numbers between two nucleons. When a proton and a neutron exchange a virtual pion, what is really happening at the quark level is that quarks and antiquarks are being rearranged between the two nucleons through the gluon field that connects their internal structures. The pion exchange description packages this complicated quark-gluon rearrangement into a simple, elegant picture. One particle, the pion, traveling from one nucleon to the other. This is why pion exchange works so well, and also why it has limits. It works because at nuclear distances, 1 to 2 femtometers, the most important contribution to the residual strong force comes from the exchange of the lightest possible color-neutral quark-antiquark system, which is the pion. The pion's small mass means it can travel the farthest as a virtual particle, so it dominates the long-range part of the nuclear force. This is the part that matters most for nuclear binding. But at shorter distances, below about half a femtometer, heavier mesons and more complex quark-gluon effects become important. The simple one-pion exchange picture is no longer sufficient. You need the full machinery of QCD to describe what happens when two nucleons are pushed very close together. The analogy with electromagnetism and van der Waals forces is remarkably precise. Electromagnetism is the fundamental force. The van der Waals force between neutral atoms is a residual effect of electromagnetism. It is weaker than the fundamental force and has a much shorter range. Similarly, QCD is the fundamental strong force. The nuclear force between color-neutral nucleons is a residual effect of QCD. It is weaker than the fundamental color force between quarks and has a much shorter range. The fundamental color force is so strong that it confines quarks permanently. The residual nuclear force, while enormously strong by the standards of electromagnetism or gravity, is actually a pale shadow of the force operating inside each nucleon. The nuclear force is the faint residual glow of the overwhelmingly powerful color force, leaking through the color-neutral walls of protons and neutrons. This layered architecture is one of the most beautiful features of how nature is organized. Physics operates differently at different scales, and each scale has its own effective description. At the scale of atoms and molecules, the relevant force is electromagnetism, and the relevant particles are electrons, protons, and neutrons treated as simple objects. You do not need to know about quarks to do chemistry. At the scale of the nucleus, the relevant force is the residual strong force, and the relevant particles are protons, neutrons, and pions. You do not need to know about gluons and color charge to calculate nuclear binding energies. At the scale of individual protons and neutrons, the relevant force is QCD, and the relevant particles are quarks and gluons. Each layer is complete and self-consistent at its own scale, while being explained by a deeper layer beneath it. The pion sits at the boundary between two of these layers. It is a composite object made of quarks and antiquarks, so it belongs to the QCD layer. But its most important role is as the carrier of the residual nuclear force, which belongs to the nuclear physics layer. The pion is the bridge between the quark world and the nuclear world. It translates the complicated dynamics of quarks and gluons into a simple, effective force between protons and neutrons. Without the pion, we would have no practical way to understand nuclear binding without solving QCD in full, which remains one of the most difficult computational challenges in all of physics. Speaking of QCD calculations, there is one more thing worth mentioning. QCD is extraordinarily difficult to solve. The self-interaction of gluons makes the equations nonlinear and fiendishly complex. The standard mathematical techniques that work for electromagnetism, perturbation theory, where you calculate approximate answers by considering small corrections to a simple starting point, do not work for QCD at low energies and nuclear distance scales. At these scales, the coupling constant of QCD, the number that measures the strength of the force, is large. The force is so strong that small corrections are not small. Every correction is as important as the one before it. The mathematical expansion does not converge. You cannot calculate. This is in stark contrast to what happens at very high energies and very short distances, where QCD has a remarkable property called asymptotic freedom. Discovered in 1973 by David Gross Frank Wilczek and David Politzer, asymptotic freedom means that at very high energies, the strong force actually becomes weaker. Quarks that are very close together, probed at very high energies, interact relatively weakly. The coupling constant becomes small, and perturbation theory works beautifully. This is why QCD was confirmed as the correct theory of the strong force. At high energies, its predictions could be calculated precisely and compared to experiments at particle accelerators. The agreement was spectacular. Gross, Wilczek, and Politzer received the Nobel Prize in Physics in 2004 for this discovery. But at low energies, at the distance scales relevant for nuclear physics, asymptotic freedom does not help. The coupling is strong. Perturbation theory fails. Calculating the properties of protons, neutrons, and pions directly from QCD requires a completely different approach. The most powerful method currently available is called lattice QCD. In lattice QCD, space and time are represented as a discrete grid of points, a lattice, and the equations of QCD are solved numerically on supercomputers. This is computationally intensive beyond anything you might imagine. Even with the most powerful supercomputers on Earth, lattice QCD calculations of nuclear properties take months or years to complete. But the results are remarkable. Lattice QCD can calculate the mass of the proton, the mass of the neutron, the mass of the pion, and the binding energies of light nuclei directly from the fundamental theory. The quark masses and the coupling constant are the only inputs. Everything else is a prediction. The fact that lattice QCD correctly predicts the pion's mass is a profound confirmation that we understand the pion's nature. The pion's mass of about 135 to 140 million electron volts is not put into the theory by hand. It comes out of the calculation. The theory takes the quark masses and the gluon dynamics as input and produces the pion's mass as output, and the answer matches reality. This tells us that our understanding of the pion as a quark-antiquark bound state, a near Goldstone boson of spontaneously broken chiral symmetry, is correct. The deep mathematical structure of QCD explains why the pion exists, why it has the mass it has, and why it plays the role it plays in nuclear physics. But lattice QCD also shows us why the pion exchange picture, despite being an approximation, is such a good one. When you solve QCD on a lattice and look at the force between two nucleons, what you see at distances of 1 to 2 femtometers is exactly the Yukawa potential. The one pion exchange description emerges naturally from the full theory. It is not a crude approximation imposed from outside. It is the dominant contribution to the residual strong force at nuclear distances, derived from first principles. The pion exchange model is QCD's own answer to how nucleons interact at low energies. It is the theory simplifying itself. Now let us step back and see the full picture. What is the pion really? It is a quark bound to an antiquark by the fundamental strong force mediated by gluons. It is a meson, one of nature's two permitted ways to build a color-neutral, strongly interacting particle. It is a near Goldstone boson, almost massless because of the approximate chiral symmetry of QCD, given its small mass by the tiny but non-zero masses of the up and down quarks. It is inherently unstable, carrying within itself a quark and an antiquark that will eventually annihilate or rearrange into lighter particles. Its charged forms decay through the weak force in about 26 nanoseconds. Its neutral form decays through electromagnetism in about 84 attoseconds. It is among the most transient objects in all of nature, And yet, this transient, unstable, self-destructing particle is responsible for the force that holds every atomic nucleus together. Virtual pions, quantum fluctuations in the pion field, are constantly exchanged between protons and neutrons inside every nucleus. This exchange creates the residual strong force, the leftover effect of QCD that binds nucleons into nuclei. The force has a range of about 1 to 2 femtometers, set directly by the pion's mass. It is strong enough to overpower the electromagnetic repulsion between protons, and it is short-ranged enough to be invisible at any scale larger than the nucleus. The nucleus does not need the pion as a permanent physical object sitting inside it. It needs the pion as a process, a continuous quantum process of creation, exchange, and absorption that generates the binding force. The pion is not a brick in the nuclear wall. It is the mortar being perpetually applied, a dynamic quantum event that never ceases. The stability of the nucleus comes not from the permanence of its components, but from the constancy of the exchange. Think about what this means for the world you experience every day. Everything around you, the ground beneath you, the air you breathe, the water you drink, the cells in your body, every single bit of it is made of atoms. And every atom heavier than hydrogen has a nucleus. And every one of those nuclei is held together by virtual pion exchange. The carbon atoms that form the backbone of every biological molecule in your body contain 6 protons and 6 neutrons, held together by the ceaseless exchange of virtual pions. The oxygen atoms in every breath you take contain 8 protons and 8 neutrons, bound by the same mechanism. The iron atoms in your blood, the calcium atoms in your bones, the sodium and potassium atoms that fire your nerves, all of them exist because of pion exchange. If you could somehow switch off the pion field, if you could stop the exchange of virtual pions between nucleons, every nucleus in the universe would disintegrate instantaneously. Every atom beyond hydrogen would cease to exist. All complex matter would dissolve into a sea of isolated protons, neutrons, and electrons. There would be no molecules, no chemistry, no solid objects, no liquids, no planets, no stars powered by nuclear fusion, no biology of any kind. The material richness of the universe, everything from the simplest helium atom to the most complex living organism, depends entirely on a particle that cannot survive on its own for even 1/1,000,000th of a second. This is one of the most profound and strange facts about the physical world. The stability of matter does not rest on stable foundations. It rests on a perpetual quantum process involving the most unstable kind of particle imaginable, a particle made of matter and antimatter, a particle that carries the seeds of its own annihilation, a particle that exists only as a fleeting fluctuation in a quantum field. And yet from this impermanence comes permanence, from this instability comes stability, from this ceaseless quantum flickering comes the enduring structure of the material universe. There is a lesson here about how nature builds complexity. Nature does not build from the top down, using stable, permanent, easily understood components. It builds from the bottom up, using layers of effective description, each layer emerging from the dynamics of the layer beneath it. Quarks and gluons produce protons and neutrons through the confinement of the fundamental color force. Protons and neutrons produce nuclei through the residual strong force carried by virtual pions. Nuclei and electrons produce atoms through the electromagnetic force. Atoms produce molecules through chemical bonding. Molecules produce cells through biochemistry. And cells produce organisms through biology. At each layer, the relevant physics is different. The particles are different. The forces are different. The rules are different. And at each layer, the physics of the layer below is hidden, packaged away, inaccessible except through its residual effects. Chemistry does not see quarks. Biology does not see nuclear forces. You do not see pions. And yet every layer depends on the layer beneath it. Pull out any layer and everything above it collapses. The pion is a perfect example of this layered architecture. It exists at the boundary between the quark-gluon world and the nuclear world. It is a creature of QCD, built from quarks and antiquarks and bound by gluons. But its most important role is in nuclear physics, where it serves as the carrier of the residual force between nucleons. It translates the deep, complicated, non-linear dynamics of quarks and gluons into an elegant, effective force between protons and neutrons. Without it, or more precisely, without something playing its role, the two layers of physics would not connect. The quark world would have no way to produce bound nuclei at the nuclear scale. The pion is not the final explanation of the strong force. QCD is deeper. The pion is an effective agent, a messenger, a translator between layers of physical reality. But that does not make it less important. If anything, it makes it more important. The pion is the mechanism through which the fundamental strong force manifests at the nuclear scale. It is the channel through which confinement and chiral symmetry breaking produce the binding of atomic nuclei. It is the reason that the quark-gluon dynamics deep inside each nucleon have consequences for the large-scale structure of matter. And perhaps the most remarkable thing of all is this. You are made of atoms. Those atoms have nuclei. Those nuclei exist because of virtual pion exchange. The pion is a quark-antiquark pair, matter and antimatter bound together, flickering in and out of existence on timescales so short that light barely moves a distance smaller than a virus. And this fleeting, impermanent, self-annihilating quantum whisper is the reason you exist. It is the reason stars shine, the reason planets form, the reason chemistry happens, the reason life is possible. The most permanent structures in the physical universe owe their existence to the most impermanent particle in physics. The next time someone tells you that the universe is made of atoms, you will know something deeper. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. And the force holding those protons and neutrons together inside the nucleus is carried by the pion, a particle made of a quark and an antiquark, a particle that cannot survive on its own, a particle that exists only as a quantum fluctuation in a field. The universe is not built on solid foundations. It is built on quantum processes, on ceaseless exchanges, on the perpetual flicker of particles that are born, serve their purpose, and vanish. And from that flicker, everything you know emerges. Every mountain, every ocean, every star in the sky, every thought in your mind. All of it held together at the deepest level by a quantum whisper that never stops.